All right, let's dive into an unseen world that's happening all around you right now. We're talking about what happens when waves collide, a concept called superposition and interference. It's the physics that explains how a tiny whisper can travel across a giant, noisy room, and also how your headphones can create total silence out of thin air. Let's get into it.
So here's our plan for this explainer. We're going to start with a weird sonic mystery, then unpack the physics of what happens when waves collide. After that, we'll uncover one of light's biggest secrets, see how these patterns pop up everywhere, and finally, we'll decode the patterns themselves and test what you've learned.
So first up, let's start with a puzzle that seems to completely defy the laws of common sense.
Okay, picture this. You're at Grand Central Terminal in New York, standing by the famous Whispering Wall. You can face a corner, whisper something super quiet, and your friend on the complete opposite side of the archway, over 30 feet away, can hear you clear as a bell, even with all the chaos and noise of the station. How on earth is that possible? Well, the answer isn't magic, it's all about how waves play together.
And that brings us to the core concept that makes it all happen, the principle of superposition.
I know that sounds super technical and maybe a little dry, but the idea is actually really simple. When waves meet, they don't crash into each other like cars. They just pass right through one another. But for that one tiny moment when they're in the same spot, their energies combine. And that means they can either boost each other up or they can completely cancel each other out.
And this slide shows those two possibilities perfectly. Over on the left, that's constructive interference. See how the peaks of the waves line up with other peaks? They're in sync, so they add together to make one big, powerful wave. But look at the right. That's destructive interference. The peak of one wave meets the valley, or the trough, of the other. They are perfectly out of sync, and poof, they cancel each other out, leaving absolutely nothing.
And this isn't just a theory, it's technology you probably use every single day. Your noise-canceling headphones are little masters of destructive interference. There's a tiny microphone on the outside that listens to the annoying background noise, right? The headphones then instantly create an exact opposite sound wave, what we call an anti-sound wave. This anti-sound is played into your ears, it meets the real noise, and they cancel each other out. You're left with beautiful silence. So yeah, they're literally fighting sound with more sound. How cool is that?
So we know waves can add up and cancel out. We see it with sound, with water, but what about light? Answering that question led to one of the most important, most revolutionary experiments in the entire history of physics.
So back in the early 1800s, there was this huge debate going on. Was light a stream of tiny particles, or was it a wave? A brilliant scientist named Thomas Young came up with an incredibly elegant experiment to figure it out once and for all. He thought, hey, if light really is a wave, then it should interfere with itself, just like water waves do.
And here's the setup he used. It's genius in its simplicity. Young took a single source of light and shone it at a barrier that had two tiny parallel slits in it. The whole trick here is that as the light passes through those two slits, it's like you're creating two new, perfectly synchronized light sources. In physics, we call that being coherent. Now you've got two sets of waves that can spread out, overlap, and interfere.
And this was the moment of truth. If light were particles, you just expect to see two bright lines on the screen behind the slits. But that is not what Young saw. Instead, he saw this incredible, shocking pattern of alternating bright and dark stripes. The bright bands, that's where the waves were interfering constructively. The dark bands, that's destructive interference. This experiment was the smoking gun that proved light behaves like a wave.
Now, to get a really nice, stable pattern like this, there are a few rules you've got to follow. The light sources have to be coherent, which just means they need to stay in step with each other. The waves also need to have the same frequency, which for light means they need to be the same color. And here's a fun little bonus fact. If you use white light, which is actually a mix of all the colors, you get a bright white fringe right in the center with these beautiful rainbow-colored edges.
And here's the really amazing part. This whole interference thing isn't just a special trick that light does. It's a fundamental property of all waves.
For example, you can set up two speakers playing the exact same musical note. If you walk in front of them, you will physically move through an interference pattern. You'll hear the sound get really loud in some spots, that's constructive interference, and then eerily quiet in other spots where it's destructive. It's Young's experiment, but for your ears.
You can even do this with invisible waves, like microwaves. If you use a microwave transmitter and a double slit, a special probe can detect a very clear pattern of high-energy spots, or maxima, and zero-energy spots, or minima. It just goes to show you how universal this behavior is for anything that acts like a wave. Okay, so we've seen that these patterns happen, but can we actually predict them? Can we do the math? Absolutely. Let's take a look at how we can decode these interference fringes.
Believe it or not, it all comes down to this one simple, elegant formula. Here, x is just the width of those bright fringes, or the distance between them. It depends on the light's wavelength, which we call lambda, the distance from the slits to the screen, which is d, and it's divided by a, which is how far apart the slits are. So basically, a longer wavelength or a farther screen will spread the pattern out, and putting the slits closer together also spreads it out.
So let's just plug in some real numbers to see how it works. Say we're using light with a wavelength of 600 nanometers. The slits are 0.5 millimeter apart, and our screen is 0.8 meters away. You just pop those values into the formula, crunch the numbers, and what do you get? You get a fringe width of 0.96 millimeters. The math tells you exactly what the pattern will look like. It's incredibly predictable.
All right, I think you're getting the hang of this. So let's solidify these concepts. We're going to run through a couple of quick questions just to test your understanding. Ready?
Okay, let's try working backwards. This time, imagine you've done the experiment and you've measured the pattern. You see the fringes are 0.5 millimeter apart. Can you use that information to figure out what kind of light you were using? What was its wavelength? All you have to do is rearrange that formula to solve for lambda.
And the answer is 625 nanometers. That corresponds to a reddish-orange light. So by just rearranging the formula, you can turn this whole experiment into a tool for actually measuring the properties of light itself. Pretty powerful stuff. All right, one last question to bring it all home. Let's get back to the absolute core principle. Imagine you have two identical waves. Each one has an amplitude of 2 centimeters. What's the resulting amplitude when they interfere constructively and when they interfere destructively? When they interfere constructively, their powers combine. The amplitudes just add up. So 2 centimeters plus 2 centimeters equals a big 4 centimeter wave. But when they interfere destructively, they subtract. 2 minus 2 is 0, nothing. That simple act of adding and subtracting is the foundation for everything we've talked about today.
And that pretty much wraps it up. From sound and light to microwaves, this interference is a fundamental process that's constantly shaping the world we experience. So the next time you pop in your noise-canceling headphones or you see those shimmering rainbow colors on a soap bubble, you'll know it's all part of this incredible, unseen dance of waves. Thanks for joining me.